Enthalpy balances are common techniques used to get us equations that we can use, such as in process control, to evaluate systems based on certain conditions and be able to react to changes or perturbations. And in this video, I will discuss how we can go through deriving a general enthalpy balance on a stir. And to do that, I will draw a mixer. And in this mixer, we will have two streams coming together. Stream 1 will have some temperature T1, a mass flow rate W1, and a composition X1. Stream 2 will have some temperature T2, a mass flow rate W2, as well as a composition X2. And inside the stirrer, they will be well mixed. And exiting our stir will be some stream with a temperature T, a mass flow rate W, and some composition X. And another thing I will add in here is, because we are keeping things general, we may have some kind of heat being added to or removed by our system, and we can also be performing work on our system. And note the dot on top of these refers to a time component, so this would be joules of heat added per time for Q, or work done by or on the system per time for W dot. And so what I'll do now is talk about the enthalpy, the general enthalpy term, which we abbreviate as H. So H is equivalent to the integral of m times Cp times dt from some reference temperature to some final temperature, or whatever temperature your stream is at. And at this point, I would like to note how it's common in chemical engineering classes, we can sometimes assume that Cp is a constant. So if our temperature fluctuations are low enough in our system, we can neglect the heat capacity, specific heat capacities, temperature dependence. And in situations like those, we can pull out that term. And in terms of the mass of the system, as we recall, mass is equivalent to rho times V, the density times the volume of our system. If density is not a function of temperature, which if we wanted to be very accurate in our models, we can take that into account, we would leave m inside our integral, or volume can also be a function of temperature, in which case we have to take that into account. But in introductory courses, typically we'll be able to neglect these variations and temperature dependencies. So as many of us will remember from general chemistry courses, we can just say H is equal to mCp delta T. And this holds some of the time. And as we'll learn in thermodynamics courses, it's often, this is a safe assumption when we're working with small temperature variations, but we need to be more thorough and precise when we're working on large order systems. We want to have higher degrees of precision. So this, do not make this assumption unless you're absolutely certain you don't need to take those things into account. And another thing I would like to note before jumping into the actual enthalpy balance is something referred to as specific enthalpy. And specific enthalpy is written as H hat. And H hat will have units of some energy, so we'll call it joules per mass, like kilograms. And it is defined to be the same thing, and we just divide both sides of our equation by m, which would be from integral T ref to T of Cp dt. So knowing these two relationships are very important before making an enthalpy balance. And so what I'll do now is go through how we can set up a general transient enthalpy balance, in which case we're not assuming a steady state. And as with anything in chemical engineering, accumulation is equal to in minus out plus generation and consumption. And in this case, what we'll be analyzing is how enthalpy in our system evolves with respect to time. In that case, our accumulation term would be equal to dH dt, and that will be equivalent to whatever enthalpies we have coming into our system. And what we'll note is we'll be able to say this will be equivalent to the specific enthalpy of stream 1 times the mass flow rate of stream 1, and this should make intuitive sense because we will have units of energy per mass times mass per time, and this will have units of mass energy per time. So the dimensions will agree. And also coming into our system, we will have the specific enthalpy of stream 2 times the mass flow rate of stream 2. And leaving our system, we will have some value, the specific enthalpy of our exiting stream times the mass flow rate of the exiting stream, W. And we will also have a Q term, Q dot term, to represent any energy we are taking into or out of our system. If we had some not well insulated system, we could place that term into here, the heat that's being lost to the surroundings, like so. Or if we had a heater integrated into our system, that's where we could put it in this equation. And we also have the possibility of performing work on our system, and that will have a quantity W dot. And so this concludes a general enthalpy balance that we can do in process control or thermodynamics. And I hope you guys find this useful. Let me know if you have any questions, and thank you for watching.